HCl a strong acid and HF not. Then we're going to look at these guys down here that we call the oxy acids. We call them oxy acids because they're acids, they contain hydrogen, but those hydrogens are bonded to oxygens, and we're going to talk about why are some of them bases, some of them weak acids, and some of them alcohols. Now guys, in order to do this, we've got to start here, and this is where you want to start taking notes. We are going to talk about something called the H star bond. H star. So what is the star? Well guys, the star simply refers to something else. It could be a molecule, it could be an atom. But guys, what we're going to do is we're going to have this entire conversation by focusing on the bond that exists between hydrogen and something else. So, what we need to talk about then, guys, is the three factors that we've got to keep track of when we're trying to figure out if hydrogens will be acidic or basic, tied to OH, or neither, which makes them alcohols. So again, the big idea here, guys, is all of these compounds contain hydrogen. The question is, what do they do with their hydrogens? And to figure that out, you need to pay attention to this bond. And there's three things that you need to pay attention to. The first is the polarity of the bond. So guys, what do you remember about polarity? What are the things that come to mind when you think polarity? Electronegativity differences. And so can you even picture the electrons moving towards the more electronegative element? We call that imbalance a dipole. We had the huge unit on intermolecular forces. You guys okay with polarity? Okay, now predict. So guys, if we've got a highly polar bond with hydrogen, or if we've got a less polar bond with hydrogen, which one would be the more acidic hydrogen, the highly polar or the lower polarity bond? The higher the polarity. And so guys, the idea is this, that the more polar the bond is, the stronger the acid will be. So now you're thinking to yourself, well, yeah, that makes sense because, and you guys all understand this, what has to happen to that H star bond in order for something to be an acid? It has to break, right? Because I should have mentioned, all of this conversation is founded on the idea that that bond's got to break to give away a hydrogen, right? So now you're thinking to yourself, well, yeah, this makes sense because the more polar the bond is, the weaker the bond is, the weaker the bond is, the stronger the acid will be. Guys, that's not necessarily the case. The next thing we need to talk about is the strength of that H star bond. So now let's talk about the relationship. What about strength will create stronger acids? Will strong bonds be strong acids or weak bonds be strong acids? Weak bond, strong acid, or strong bond, strong acid? Why would the weaker bonds create stronger acids? Because it breaks more easily and gives off more hydrogens. So the weaker the bond, the stronger the acid. And then guys, the last thing that we need to keep track of is the stability of the conjugate base. So when that bond breaks, we understand that the hydrogen goes away and whatever's left behind is the conjugate base. Well, the strength of an acid can also be impacted by the stability of what's left over. So if the thing that's left over is really stable, it's going to be a stronger acid because it's not going to want to jump back with the hydrogen. So the more stable the conjugate base, the stronger the acid. Is what? Fluorine? We're not even going to talk about the stability of fluorine. That's not, yeah. And that brings us to the next point. Guys, understand that when we now apply these three ideas to real life situations, we don't apply them in all cases, because in many cases they don't matter. So stability is actually such a secondary factor in terms of, you said fluorine, that we don't even consider it. So guys, understand that what we're going to do now is we're going to look at like HCl and HBr, and we're going to talk about why HCl is a stronger acid than HBr or HF. Well, HF, sorry. And it has nothing to do with stability. And then we're going to talk about the oxy acids, and you're going to find that those have other factors that play into it. So you need to understand these are the three things that impact the strength of an acid, but they don't apply equally in all circumstances. So that's what you've got to figure out, is which factors count in which settings. So guys, are you all caught up with me? Setting number one is this. They're called binary acids. So guys, you know that bi means two, right? So I don't know if you even need to write this down. A binary acid is just an acid that's composed of a hydrogen and one other type of atom. Many times it's a halogen, HBr, HI, HF, HCl. So we call these things HX acids. Well, these are all molecules, right? So they all fulfill the octet rule. Yeah. Okay. So guys, let's just lay it out there and then let's talk about it. What is the major predictor for the strength of a binary acid? The answer is bond strength. The strength of the binary acid depends most on the strength of the HX bond. You guys okay? You with me so far? So guys, go back and look up at your notes then relative to strength. What's the relationship? Strong bonds, strong acids, or weak bonds, strong acids? Weak bonds, right? So if you need to rewrite it, you can. I wrote it in the opposite, but you understand the logic. The stronger the HX bond is, the weaker the acid will be. Would it be easier if I wrote it in the same? If I said, you're okay, you get the idea, right? Okay, so guys, with that said, what then, and I know you see that this is where the conversation is going, what then determines the strength of that bond? Well, I would suggest that maybe you do this, and I'll bet you'll figure it out. Guys, let's do the two that we looked at. Let's go HCl, and let's go HF. And guys, what we're going to do is we're going to draw the Lewis dot structures for these two molecules, but we're going to draw them in sort of a funny way. Not funny, but we're not just going to draw the valence electrons. We're going to draw all of them. So guys, if we were to draw a kind of a complete, if you will, Lewis dot structure, if we take a look at HF, it would look like this. So we've got fluorine, and we've got the first energy level with 2 electrons, and then we've got the second energy level with 1, 2, 3, 4, 5, 6, 7, and then along comes our hydrogen, and that would be sort of like our Lewis dot structure for HF. See what I did? Am I okay? Okay, then let's do something similar for HCl. So guys, we're going to go Cl, and we've got the first energy level with 2, and then we've got the second energy level with 1, 2, 3, 4, 5, 6, good heavens, I'm struggling, 7, 8, and then we get down here with this energy level, and we've got 1, 2, 3, 4, 5, 6, 7. Remember when this actually used to be the way you drew Lewis dot structures, like in 7th grade biology? Yeah. Have you forgiven your biology teachers for even teaching this to you? And then like that. So guys, now we can experientially ask and answer the question. So guys, from experience, which is the stronger acid, HCl or HF? So HCl is the stronger acid. So now guys, let's relate that to bond strength. So if HCl is the stronger acid, what do you know about the strength of this? We'll call it bond 1 compared to this, the strength of bond 2. Which bond is stronger? Bond 1 or bond 2? Bond 2 is stronger. Does that make sense? This bond is stronger, therefore it doesn't break as easily. Therefore, this is a weaker acid. This bond is weaker, breaks more readily. Therefore, this acid is stronger. You okay with that logic? Now let's talk about why. Fundamentally, how is this molecule on the left different from the molecule on the right, making that bond weaker and the acid therefore stronger? Which changes what? Why would that additional energy level change the strength of the bond? Go ahead, Joel. It's all about shielding. Guys, this molecule, this atom is physically bigger. And remember we talked about the region of increased electron density. Well, guys, this region of increased electron density is so much further away from this nucleus. We think of that as shielding. It's so much further away that this bond is weaker, and therefore it breaks more easily. So guys, how do we condense that down then to a guiding principle? And fundamentally, guys, it's all about the size of X. So let's pull this relationship together. Remember, this is our X, chlorine, and this is our X, fluorine. And Joel's right that it's all about shielding, but let's make it simpler than that, because shielding is really a function of size. So what is the relationship? Big atoms or small atoms? Which one makes stronger acids? Big atoms. And guys, that is the relationship that you need to keep track of. Within a group, the strength of this bond weakens with size. So the bigger the atom, the weaker the bond, the stronger the acid. Did I include that? Would it be helpful if we added making a stronger acid? So equals stronger. Good heavens. I can't type.
So yeah, the size of X is negatively correlated with the bond strength. Which
The
is
size of
correlated with acid strength.
Yes. So the bigger the atom, the stronger the acid. You buy it? And the reason bigger atoms make stronger acids is because they make weaker bonds. Groovy? Okay. No, let's just leave it at that. Do we have to do a so? We're going to do it. We'll do a so in a minute. So guys, what about this? As we just drew on the paper, which one's a stronger acid, HCl or HF? HCl. But what about this? Which is a stronger acid, water or hydrogen sulfide? We haven't really thought about it that way, have we? So guys, let's take a look. So here we've got oxygen, water. Here we've got sulfur. So which one's going to be the stronger acid, H2O or HS? HS. Sulfur is bigger than oxygen, so the bonds that sulfur forms with hydrogen will be weaker, and consequently they will fall apart more easily, so H2S is a stronger acid. Does that make sense? Yeah.
In comparison with hydrofluoric acid, the hydrofluoric acid and the other halogen strong acids, this hydrofluoric acid it is small enough and its bond is strong enough that it just doesn't quite make the...
Yeah, it doesn't break apart readily enough for it to form a strong acid. Yeah, that bond is so hard to break. Yep, you got it. Yeah, Anna. Wait a second, what do you mean in a row? You mean in a not a column but a row? That's what we're going to talk about now. So guys, understand that this takes care of the issue when we deal with groups, right? But what about periods, rows? What about the periods? Well guys, then the major predictor is no longer bond strength, it's now bond polarity. And this is still binary acids. So guys, when you are talking about a period, a row, when you're talking about a period, the major predictor is no longer the strength of the bond, it's the polarity of the bond. The reason is because these atoms are functionally about the same size and therefore have about the same bond strength. So then it becomes a question of polarity. And guys, remember, what does polarity depend upon? Electronegativity. And remember the trend. As we move to the right, what happens to their electronegativities? They become more electronegative, making the bond more polar, making the acid, look up at your notes, more polar bonds form stronger acids. So guys, as we move left to right, the electronegativities go up, the bond becomes more polar, and the acids become stronger. So there's the relationship there. So guys, summarizing that, the strength of the acid increases as the electronegativity of X increases, and we understand that as we move to the right, they become more electronegative. And that's what we need to talk about last, is what's the tiebreaker. And I'm going to put you in that position in just a second. You guys all caught up with me? So guys, what about this? Which is stronger? Which one of these will be a stronger acid? Is it NH3 or CH4? So now you'll notice they're in the same group, right? So they have carbon and nitrogen are pretty much the same size. So it's not a bond strength issue because they're in the same group or in the same period. So guys, which one will form the stronger acid? Carbon to hydrogen or nitrogen to hydrogen? Nitrogen to hydrogen, because nitrogen is more electronegative, that bond is more polar, therefore it is more susceptible to breaking. So NH3 will be our stronger acid.
But what about the difference in the hydrogens? Does that not matter?
They're all hydrogens.
No, there are 3 hydrogens.
Doesn't matter. It's because they don't break in groups of bonds, they break one bond at a time.
Okay.
Yeah, go ahead, Talmadge.
NH3 is not usually a base.
Right, but if we're doing it comparatively,
CH4 is not a base.
is neither, right? But understand that they, and this is, so when we talk about, you look at NH3 and you go NH3 is a base. But the reason that you think of it as being a base is because it's basic in comparison to water. And guys, we haven't directly said this, but we should talk about it. When we say something is an acid or something is in a base, it's always assuming that it's in comparison to water. So we think of things as acids if they give away hydrogen to water. We think of things as bases if they take in hydrogens from water. We can still, though, talk about this. We think of NH3 as a base towards water. We think of CH4 as being neither towards water, but we can still comparatively talk about what they do compared to one another, and this is more likely to give away hydrogens than that. Good. So let me repeat what Talmadge just said. In some mixtures, CH4 can function as an acid. It's just that that mixture isn't with water because water can't pull hydrogens off of it. It would have to be something that has a greater affinity for protons than water does. Yeah, great point. You guys good? So now do this one. So guys, we've got NH3 and SiH4. See the problem? Yeah, so here we've got our nitrogen, and here we've got our silicon. And so guys, based upon their position in groups, or their position in periods, nitrogen is to the right, so it will be more or less electronegative. More electronegative, so we would expect that to be the stronger acid. But then when we go down, we know that silicon is below nitrogen, which means silicon is bigger, therefore its bond with hydrogen would be weaker, therefore we would think that silicon would be the stronger acid. So guys, which one predominates? Is it polarity based on electronegativity, or is it bond strength based upon size? The answer is bond strength based upon size. Guys, the strength of a binary acid is more dependent on bond strength than it is on bond polarity. So silicon tetrahydride would be your stronger acid. Yeah.
So that means that H2S is a stronger acid than
H2S.
If you had a sulfur acid.
Yeah. I would love to look up Ka values, but if someone had a gun to my head, I'd say yes. Yeah, I've never looked at it, Mark, but yeah.
Hydrofluoric acid is that strong, relatively speaking.
Well, the thing that's scary about, that's not scary, well, it is scary. The thing that's interesting about HF is that not only does it give away hydrogens, making it acidic, but the fluorine that it produces when it protonates is also crazy reactive. So a lot of the craziness of hydrofluoric acid is a function of the fluorine and not just the hydrogen.
Because fluorine has such
Because it's so electronegative, yeah. But Mark, I'd love to look that up. Let me bookmark that in my brain. So Ka's for H2S, Jake, I figured you'd already be looking it up. And no, it's good. We'll look it up later. Okay, you're always Johnny on the spot with your phone. Okay, so guys, we are now done with binary acids. You guys comfortable with that last sentence? You guys good? Okay, so now guys, we're gonna shift gears. We're going here. Oxy acids. So guys, what I'm about to share with you is nowhere in the notes, but this is really going to help your thinking on this. Do this with me logically. I can't figure out how to put this in print, so it's better for me to just freehand this. So guys, oops, let me pick a color that stands out. So an oxy acid is this. It's a hydrogen bonded to an oxygen. Thus the name oxy acid. Now I'm just going to lay this out there for you, and I'm going to ask you to figure out why. The strength of an oxy acid has nothing to do with the strength of the bond. Because they're all the same. Was that you, Joel? Yeah, why? Why are they all the same? Because it's always bonded to oxygen. So guys, this bond always has the same strength because it's always bonded hydrogen to oxygen. So when you're thinking about oxy acids, it never, you may want to write this down, it never depends on bond strength. And again, Brandon's right on it. The reason it never depends on bond strength is the hydrogen's always bonded to an oxygen. And we learned previously that the strength of the bond is a function of the size of the thing the hydrogen is bonded to. And if it's always an oxygen, its size doesn't change, and therefore the bond strength doesn't change. So if bond strength is not the deal, what does it have to be? Polarity, and then also the stability of the conjugate base. So guys, with the oxy acids, it is always a function of polarity. So let's flesh this out. So you guys get this, right? Oxy acids are write it down if you need. And guys, I'm just sort of teeing this ball up here. So the idea is this: oxy acids are always hydrogens bonded to oxygens, but we've got this problem that these also exist in bases. So what determines if these things will be acidic or basic or even alcohols? Well, guys, it all has to do with what they're bonded to. So we're now going to introduce this idea of Y. We said binary acids are HX. Oxy acids are YOH. So, whether an OH group is acidic, basic, or an alcohol is all about Y. So guys, in order for this to be a base, what does Y have to be? Think about the things that you know that are bases with OH. NaOH. LiOH. Metals. Guys, if Y is a metal, this is a base, because metals have low electronegativities. Because metals have low electronegativities, guys, what does oxygen do to Y if Y is a metal? Oxygen's got a high electronegativity. Y has got a low electronegativity. So what is oxygen going to do to Y if Y is a metal? Steal its electrons. What kind of bond does that form? An ionic bond. So guys, if Y is a metal, then this bond is ionic. And if it's ionic, we have now formed OH groups, and those are basic. Was that too quick? So guys, let's go back through this. The idea is this: if Y is a metal, metals are big and fat and weak. If metals are big and fat and weak, oxygen's going to steal electrons from it, making Y a positive ion and making OH a negative ion and making the bond between them ionic. At that point, when this thing breaks apart, it's the ionic bond between the metal and the OH that will dissociate, producing OH and making this basic. Does that make sense? And guys, experientially, you knew that. What are the bases? They're the metal hydroxides. So if Y is a metal, this will be a hydroxide, and that forms a base. You good with that idea? Can I move on? Okay, so guys, what if Y is a non-metal? Well, guys, if Y is a non-metal, let me write it down for you again. If Y is a non-metal, then what is this bond going to be? Ionic or covalent? Covalent, because if Y is a non-metal, it's strong. And if Y is strong, oxygen can't steal from it, and consequently, that's a covalent bond. So if that's the case, this YO bond is going to be covalent, and as a result, hydroxide is not going to be formed. We don't have a transfer of electrons because oxygen can't steal from a non-metal. So we don't have a transfer of electrons, so we don't have any OH. So we're not going to get bases. So these will either be acidic or they will be neutral. And if they're neutral, maybe I don't know if this is obvious or not. Let me include it. Exactly. If they're neutral, they are alcohols. Oops.
I feel like we're almost doing a form of, do you remember that lab we did in November where we had to create that massive list of the same procedure?
Yeah, right. That's what you're classifying things. Yeah. Yep. So guys, what then determines if these things will be alcohols or if they will be acids? And this is a new concept that you're going to want to scratch in your notes. It has to do with something called drift. And guys, drift is an accepted term that you can use on the AP test. The AP graders and the AP authors understand what you mean when you say drift. So what is drift? Well, guys, remember we have already identified that the strength of these oxy acids is not dependent on bond strength because they're all bonded to oxygen. So then it becomes a question of polarity. Polarity is a function of electronegativity. But all these hydrogens are bonded to oxygens, so they also have a fixed electronegativity. But it turns out, guys, it's not the electronegativity of the oxygen that matters, it's the electronegativity of what's on the other side. So the idea is this: as the electronegativity of Y goes up, and if this is seeming murky, I'll show you a picture and it'll all make sense. As the electronegativity of Y goes up, the acidity increases due to drift. Because what happens is the OH bond becomes more polar. And remember what we said. More polar bonds break more easily, making a stronger acid. So guys, what on earth are we talking about? Well, check this out. And Brandon, this is actually one of those acids that we talked about in that homework question. Remember? Yeah, it's right there. So guys, the idea is this, sort of, and you don't need to draw this obviously, but sort of reason through this with me. So guys, here we've got an OH and here we've got an OH. So this bond right here and this bond right here have the same strength. How do we know? Because they're both oxygens. They have the same size. But now, guys, we might also be thinking that they have the same polarity, because this is an oxygen and this is an oxygen, and we know that polarity is a function of electronegativity difference, and if this is an oxygen and that is an oxygen, we might then be thinking not only do they have the same strength, but they also have the same polarity. And that would be true except for this. Guys, it turns out that the polarity of these bonds is not just determined by the electronegativity differences between the oxygen and the hydrogen. It turns out that chlorine and iodine also get in on the game. And so chlorine, which is a relatively electronegative element, reaches past the oxygen and drags on these electrons, literally pulling, remember this electron pair, literally pulling these electrons closer to the oxygen and making that bond more polar. Now guys, iodine is less electronegative. Its electronegativity is 2.5 compared to 3. Iodine's less electronegative. So iodine reaches past the oxygen and causes these electrons to drift as well, making that bond more polar. But guys, the difference is because iodine is weaker, it doesn't drift as much. So the idea then is that stronger chlorine causes these electrons to move further, making it more polar. Weaker iodine does that less, so this bond is more polar than this bond, and this more polar bond breaks more readily. And you can see that that actually makes HClO 1,000 times stronger than or whatever. This guy is 1,000 times weaker than that guy. Yeah. Or are you just scratching that? Does that make sense? But guys, notice their Ka values. 10 to the negative 8th and 10 to the negative 11th. Neither one of them is very strong. But this is 1,000 times stronger because of the drift that's created, or I'm sorry, this is 1,000 times stronger because of the drift created by that stronger chlorine. Yeah. Okay, so the idea is this. Let's sort of draw it. So we've got a pair of electrons right here, right? And those electrons are closer to the oxygen than the hydrogen. Why? Because oxygen more electronegative. But hold on, don't look away. It gets even better than that, because these electrons are closer to the oxygen because it's stronger than hydrogen, but they're even closer to the oxygen because of chlorine. So it's not just the oxygen pulling on these electrons, it's also the chlorine. And this chlorine is pulling on these electrons and moving them even closer to the oxygen than they would be if the chlorine weren't there. Well, turns out iodine does the same thing. Iodine also pulls on those electrons, but the pull of iodine is less than the pull of chlorine, moving the electrons even closer. What are you doing? Moving the electrons, no, stop. moving the electrons even closer, making that more polar.
So, but doesn't that chlorine, the electrons between chlorine and oxygen,
Doesn't matter.
they don't cause
Don't even think about it. You're just thinking about, all you have to understand is that chlorine is stronger, moves those electrons further than happens here. That's all you have to know. Chlorine is more electronegative, reaches around the oxygen through this thing called drift, pulls them closer. That's all you got to know. Go ahead, Talmadge.
So I thought that you could only have alcohols if it was an OH paired with like
It is, and that's the idea that, and we're about to look at that. The idea is that carbon is such a relatively low electronegative element. So we can even do that.
there aren't other atoms that are also that low electronegativity that you must have.
Yeah, but we don't call, the reason that we care about alcohols is because alcohols are what are called an organic functional group. Organic means contains carbon, and we're going to talk about these in test review. Carbon's really important. And so we talk a lot about carbon and things that bond to it. So if you've got a carbon bonded to an OH, that's called an alcohol. But we could replace the carbon with a nitrogen, and that would also not break apart. We just don't give it a name. It functions yeah, that's a great point. We could just as easily talk about NOH, and nitrogen's not electronegative enough to cause the drift and make the bond polar either. We just don't give it a name because no one cares, because life isn't based on that. Yeah, exactly. So, are we good? Jake, do you have something to contribute, or are you just being distracting? Oh, good. Okay. So, guys, you okay with this idea? Okay, so guys, this is about to become very important depending upon what you want to invest the rest of your life in. Because guys, if you, hold on. I forgot to animate that. Yeah, the lone. So, hold on. I redrew this, so I need to redo this. Okay, here we go. So guys, the idea is this. We are now going to talk about a very special case of this idea of neighboring atoms creating drift. So guys, many times this atom Y can be bonded to other oxygen atoms, and this creates drift as well. So guys, the idea is this. These oxygen atoms that are not Y, but they're bonded to Y, can make this OH bond even more polar, creating even stronger acids. And so guys, the example that you need to understand is this. Check this out. So, here we've got an O and an H. And guys, if this element Y is strong, it'll create drift, and this will become a stronger acid. But guys, this can also create a stronger acid. Tag another oxygen onto there. And now guys, we get really interesting drift going on, because what happens is this oxygen can actually pull on those electrons. And that can further polarize that bond and create substances that are acidic. Go ahead.
So what if we have like a nitrogen? And we have an oxygen?
Right, so what if this were a nitrogen and that were an oxygen? And the answer is that would still be acidic, because now it's the oxygen that's pulling past the nitrogen. And so what about this? So let's play this game. I can do this. Watch this. So let me go back and then go here. So what if this is a carbon? So guys, if Y is a carbon atom, will this be an alcohol, an acid, or a base? An alcohol. But check this out. Now it's an acid. And it's not because of the carbon. Guys, this now becomes acidic because this pulls around the corner, and you get drift not caused by the carbon but caused by the oxygen. So again, the idea is this, guys. If this is gone, this is an alcohol. If this is there, it now becomes an acid. Do you see it? And guys, this opens up a really interesting conversation because now we can talk about this. Remember this guy? Yeah, so if we do this, and if we add a carbon and 3 hydrogens to this, we now have acetic acid, vinegar. So guys, why is vinegar acidic? What makes it acidic? This oxygen right here. Guys, vinegar is acidic because of that oxygen right there. It would be an alcohol, right? If that weren't there, it would be an alcohol. But guys, if you do this, and if you tag a group of carbons on it like this, guess what you have now? Aspirin. And if you take this off, ooh, can I even draw this? I'm not even going to try. But if you draw a big old kinkly thing on here, guess what you have now? DNA. So guys, the deal is this. There are billions of substances in our existence that are acidic. And guys, it's everything from aspirin to vinegar to DNA, deoxyribonucleic acid, to RNA, ribonucleic acid. Guys, don't miss this, focus. Guys, there are thousands and thousands of molecules that make up the chemistry of our bodies and the chemistry of life that are acids. And it's, again, everything from DNA to RNA to lactic acid that builds up in your muscles if you're exercising anaerobically. Guys, and the one thing that all of those acids have in common is this. All organic acids contain that group. It's so important. I'm going to share the name with you in a minute. But guys, first you've got to understand what makes this acidic. And the answer is this thing right there. This group causes drift, making this hydrogen acidic. And guys, this group has a name. This group is what is called a carboxylic acid group. You may also hear it called a carboxyl group. And guys, it's just that COOH group. But this group composes the largest category of organic acids. There are other ways of making carbon-based compounds, organic compounds, acidic. But guys, 90%, 95% of the ones that you know or will ever learn, depending on your major, contain these. I mean, again, that ranges from acetic acid, which is vinegar, to formic acid, which is actually ant spit. Yeah, if you get an ant bite and it burns, actually there are these little molecules inside of ants that make formic acid. Acetylsalicylic acid, which you know to be aspirin. But guys, what is it that makes this thing acidic? So let's talk. So guys, what is it that makes this acidic? You said it, Brandon. Say it again. It's the drift, right? So guys, one of the things that makes this acidic is that this causes drift. Guys, make sure you can put this together in your head. Why does drift make this more acidic? What does that do? No, it's not bond strength. What does it do to this? Makes it more polar, therefore that bond is more likely to break. But guys, guess what? That is not the only reason that this is acidic. You ready for the other one? Do this. Draw this in your notes. Draw acetate ion. Draw the Lewis dot structure for acetate ion in your notes. Do it right now. Hold on. Do you understand why I'm having you do acetate ion? Put this together. So what I've done is I've put a CH3 COOH. So that's acetic acid, right? So CH3 COOH is acetic acid. So why am I having you do acetate ion? Take off the hydrogen and what's left is acetate ion. So guys, draw the Lewis dot structure for acetate ion in your notes. Just draw it. We'll talk. Just draw it. I'll be really impressed if any of you do this properly. My guess is you won't. So guys, what I'm having you do is draw here we go. CH3 COO, and if you count electrons, we've got 4 and 3 and 4 and 6 and 6 and 1. So that would be 7, 11, 11 and 12 is 23 is 24. So we've got 24 electrons. Let me take these off for now. So we've got 24 electrons. And yeah, it does if you do it right. So guys, we've got 24 electrons. Here we've got 2, 4, 6, 8, 10, 12, 14. So that leaves us with 10 to put on. So we've got 2, 4, 6, 8, 10. So that is the Lewis dot structure. We can put it in brackets and put the -1 charge, like so. Did y'all get that? Good, because it's wrong. If you were to write this as Lewis dot structure for acetic acid on the test, it would be wrong. Why is it wrong? It resonates. Guys, that is a delocalized pi bond. This double bond doesn't have to be there. There are 2 resonance structures of this. So guys, this is the Lewis dot structure of acetic acid or acetate ion. And we understand that it's neither of these. If you don't understand that, we need to review for the AP test. But guys, we understand that it's neither of these. That this bond that exists between the carbon and the 2 oxygens is actually a delocalized pi bond that exists partially in both directions. Well, guess what? Because it exists partially in both directions, it stabilizes this molecule, making it less reactive. Now go back to the very beginning of your notes. What are the 3 things that influence the strength of an acid? Strength, polarity, and stability. Guys, it turns out that this molecule, because it resonates, because it contains delocalized pi bonds, that stabilizes the molecule, making it less reactive, thereby making the acid stronger. Does that make sense? So when you have a conjugate base ion that is resonance stabilized, you ever notice we call it resonance stabilized? Guys, compounds, conjugate base molecules that are resonance stabilized are more stable and therefore less likely to hook back up with the hydrogen, and that strengthens the acid. You ready for the big aha? Nitrate. Guys, nitrate also resonates. And what do you know about nitrate? What's its acid? HNO3, it's strong. That is so completely stabilized as a conjugate base ion that it's worthless and it can't hook up with hydrogen at all. So this even goes to that extreme. You guys get the idea? You guys good? Okay, so gang, we got one more thing to talk about. Matt, you and I talked about this the other day briefly. We're going to do a couple seconds on this. Guys, the last thing that we need to talk about before we wrap up chapter 16 is this. This shouldn't, why does that say? Oh, yeah, okay, we can do this first and then we'll wrap this up. So guys, now we can have this conversation, coming back full circle. So let's talk. So looking at, oh boy, wait for it. There we go. Okay, so guys, looking at these two dudes right, I don't know why it's doing that. Hold on. Oh, that's why. There we go. Now can I draw? Okay, we got draw back. Now we got this 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 back. Now we got that back. Hey, there we go. Okay, so guys, back to this idea. Why did I group those two together as I'm thinking about acid strengths? They are both binary acids. And we've already talked about one is stronger, one is weaker. Why is HCl the stronger acid? Because what's bigger? Chloride is bigger. Because chlorine is bigger, it forms a stronger or weaker bond. Weaker bond to hydrogen, that makes it a stronger acid. Good? Okay. Guys, why is NaOH a base? Because Na is a metal. And guys, you got to be able to think through this. So what? Why is this a base? Because Na is a metal. How does the thinking go? Na is weak. Because Na is weak, what does O do? Steals its electrons. Because those electrons get stolen, what does that form? Ions. Na is a positive ion, OH is a negative ion. When that dissociates, the ionic bond breaks, we end up with OH, that makes it a base. Why is this a weak acid? Because of that. That's all you got to say. That is a weak acid because that oxygen, not the oxygen that's bonded to the hydrogen, but the oxygen that's bonded to the carbon creates what? Drift that makes this bond more polar, therefore making this acidic. Good? Why is this an alcohol? No ions, no drift. And as a result, that bond is strong enough that it doesn't dissociate in water and it forms an alcohol. Yeah?
So vinegar, it's an acid because of drift, but it's a stronger, weak acid because of drift.
Yes, good, yes. And I've never seen them have you tease that apart, but what you said is exactly right. You guys good? Okay. So guys, now, and Matt, this is what I was speaking of earlier, a word on Lewis acids and bases. Guys, I wrestle with this. Frankly, I decided to add it because Matt and I talked the other day. There is another way to classify acids and bases. We've got Arrhenius, we've got Bronsted-Lowry. There's one other way to classify acids and bases. It is the Lewis definition of acids and bases. Understand, guys, it is technically a part of the AP curriculum, which means you may see one or maybe two multiple choice questions on this. You will not see this in free response. But if you are going to become a doctor or a physical therapist or a dentist or a chemist, this lies in your future. And guys, organic chemistry is all about Lewis acids and bases. So I'm going to give you Lewis acids and bases in 20 seconds. You ready to go? Okay, it goes like this. And you're welcome to write this down. In order to understand Lewis acids and bases, first thing you got to do is remind yourself about this. Where have you heard of Lewis? Dot structures. What do the dots represent? Electrons. Okay, so guys, go back with me. We're going to go acids. You can write this down. You can go bases. And then we're going to go Bronsted-Lowry. What does Bronsted-Lowry say an acid does? Gives away protons. Protons are positive. What does Bronsted-Lowry say a base does? Takes in protons. Good? Okay, ready? Now let's do Lewis. Guys, Lewis wasn't focusing on the protons. Lewis is focusing on electrons, the opposite charge. So if the charge is opposite than a proton, what do you suppose is going to happen to the directions? They will also switch. So in the Lewis definition, an acid is a substance that takes in negatives. But doesn't that make sense? If it gives away positives, isn't taking in negatives sort of the same thing? And guys, in the Lewis definition, if a Bronsted-Lowry base takes in positives, it gives away negatives. So, frankly, at this point in your chemistry career, if you understand that, it's good enough. What will happen is when you get into organic chemistry, you will just become so familiar with Lewis acids and bases that you won't even have to do the translating in your head. In the same way right now that you think acid and you think give away hydrogen, because when you get into organic chemistry, very quickly you're going to be acid takes in electrons. You're not even going to have to think of it as being the opposite of Bronsted-Lowry. It'll just come to you. But for now, if you want to understand it through the lens of Bronsted-Lowry, that works. Get the idea? Okay, so guys, let me show you what this means, and this is where we're going to wrap up the day. So allow this video to wrap things up for us.
Ammonia is a base in the Bronsted sense because it acts as a proton acceptor.
Does that make sense? Guys, what do we know about NH3? It's a base, right? Why? Takes in a proton. You can picture this hydrogen moving over. And remember, anything with nitrogen tends to be a base. Now we're going to understand the Lewis definition.
Ammonia is a base in the Bronsted sense because it acts as a proton acceptor. For example, it accepts a proton from a water molecule to form the ammonium ion and hydroxide ion. In the Lewis acid-base theory, the emphasis is on the electron pair. Ammonia is a base because it acts as an electron pair donor toward the proton. The proton is an acid because it acts as an electron pair acceptor.
Did you catch that? Right, it's not the water that's the acid, it's the proton that's the acid. Interesting, right?
Lewis acid-base theory is more general than Bronsted theory because it applies to systems that do not involve protons. For example, ammonia acts as an electron pair donor toward boron trifluoride, a molecule that has a vacant 2p orbital. Ammonia also acts as a Lewis base toward metal ions, as in this example of the cobalt-3 hexamine complex. The ammonia electron pairs are donated into vacant metal orbitals. Carbon dioxide
This is great. This is all that's wrong with organic chemistry. You ready?
acts as a Lewis acid toward water. One of the unshared electron pairs on oxygen is donated to the carbon atom, as one of the CO double bond electron pairs is moved on
Catch that? The double bond broke.
to the oxygen of carbon dioxide. A proton from the water molecule moves to the oxygen of the carbon dioxide.
So guys, these are what are called electron pushing diagrams. When you balance equations in organic chemistry, you actually have to show the movement of all those electrons as the double bond breaks and then as the hydrogen moves.
Molecule, completing the formation of carbonic acid.
Oh yeah, it's ridiculous. So guys, again, you may see a couple multiple choice questions on that. Here's your homework.